All right. Hello, everyone. Welcome to Information and Coding Theory. This course is cross-listed with 2 numbers. And before we kind of get into the course material, just some kind of introductory comments about the administration of the course, about the content of the course, or the structure of the course. First, this course is entirely remote. There will not be any in-person classes. It will be taught via Zoom and Gather. Zoom we are all using and probably everyone is familiar with. Gather is something we will use for discussion sections and office hours, and the details are on the Canvas page. So if you go to the Canvas page for the course, there is a link to a separate page with the online details of the online format and access information for the course. This describes Gather, roughly what it is and kind of how to use it. We will also have all the links available in the course calendar. So if you click on the meeting, you should be able to see the relevant links for. So for each lecture, I'll use a separate Jamboard in addition to Zoom. I'll share my screen, you'll be able to see, but you can also open the Jamboard on your screen, go back and forth. And I'll kind of add the link for every lecture, maybe a few hours before the start of the lecture. Okay. The TA for the course is Gautam Rajendran, who's also on the meeting. Hey, Gautam. The timings, again, they are on the calendar in the Canvas website. In general, Canvas will be the central hub for all course-related information. All announcements, all homeworks, everything will be posted on Canvas, and all the relevant links will be available on Canvas. So make sure you check the Canvas page of the course regularly, and I'll also post announcements as needed. The discussions will be Friday 2 to 3 p.m. on the Gather space, and office hours, I will hold office hours Wednesdays 1 to 2 p.m. on Gather space. All of the times are in Central Time. In terms of more specifics about the course itself, there's no formal prerequisites, but what is kind of needed for the course is some familiarity with probability, the notions of random variables, both continuous and discrete. We'll kind of recap some of this material as we need it, but it will really help if you already are familiar with probability. If not, then some like in the course might be harder to follow. Algorithms, we won't need a lot about algorithms, but some basics of computation is helpful. What does it mean that an algorithm runs in order n square time, or what is a randomized algorithm? What does it mean that the algorithm reads a sample or sort of looks at a data or sends a message? Some basics of analysis, basic inequalities, maybe something like Cauchy-Schwarz, but maybe also some familiarity with integrals, etc., will be helpful. Not a lot, but a little bit of analysis at the undergraduate level will be useful. There is no textbook for the course. I'll be posting notes for every lecture, and as the online format page on Canvas says, it might take about a week between the time the lecture and the course notes are posted, although I'll try to do it sooner. The lectures will be recorded and also posted on Canvas. And there's some references and resources available on the course webpage. You can take a look at them. They're pointers to, and there's one useful book in particular. It's not a textbook. I won't assign things from it, but it's good to refer to. The course will have maybe 4 to 5 homeworks equally weighted. The total weight will be 60% of the grade, and a final which will be 40% of the grade. In general, in our online discussions, yeah, I'll try to make them interactive to the extent it's possible on Zoom. So please stop me at any point, just unmute yourself and ask a question if you have one. I might not always be able to monitor the chat while I'm giving a lecture, so it will be easier if you can maybe ask a question or at least raise your hand or something. And I apologize in advance if I miss. I'm also new to Zoom teaching. Okay. Let's see. Any questions about how the course will work, how to access the different parts of the course, etc.? before we get started on the actual content? Okay, and I assume everyone, when they join, they got notification the meeting is being recorded. That will be true for all lectures, not for discussions and office hours. Okay, so the course is information and coding theory. Roughly 75% of the course will be information theory, and about 25% will be codes, although this is not kind of a hard division, and also there will be parts which will be both information and coding theory. So it's and in some sense, there are many different ways of looking at information theory. It's of course, it's a theoretical basis for communication. When you're trying to send a message, how short can the message be if you want to communicate some kind of details about whatever you have in mind? If there is an error, how do you recover that? And the kind of theoretical foundation for this sort of study is information theory. It's also used in statistics for understanding various kinds of sampling algorithms in terms of how they are behaving, how much they are learning about the data. It's also used nowadays, I guess, to some extent in deep learning like settings where people kind of look at objective functions motivated by information theory. Although I should warn in advance that I'll not be covering a lot of deep learning in this course. I'll mention the information theoretic concepts, but that's about it. The treatment of information theory, here we will try to kind of combine these perspectives. And in general, I'll think of information theory as a mathematical framework for quantifying uncertainty. So and roughly what this, it's kind of something which you can view the different applications in this language. If you're trying to talk to me, until you have spoken, I don't quite know what you are going to say, and so I'm uncertain about it. And in some sense, we can measure how uncertain I am about what you are going to say. I can make maybe a reasonable guess that most people in this class, given what I have already said, if they wanted to reply to me, they will probably reply in English. I kind of have some understanding of what is the distribution of letters in English, sort of how the words sound like. So there is some amount of knowledge I have and something which is uncertain, and it's a framework for kind of quantifying the uncertainty present in this situation. And the same is true for an algorithm which is trying to learn from data. Before, the algorithm is trying to learn a model or trying to learn a hypothesis, and until it looks at the data, it is kind of uncertain. Maybe it's trying to learn certain parameters in some statistical models. So it has some maybe estimates of what things might look like, but it also, you can figure out a precise way of quantifying what it doesn't know. And as it looks at the data, it learns more, and we can try to quantify sort of how much the uncertainty changes as the algorithm looks at the data. So this is sort of a kind of broader mathematical way of thinking about information that I'll take in this course. It's useful, at least in my opinion, for communication, for statistics, and in general, that's how we will think of information. And codes, in some sense, are dual way. They are kind of so information kind of trying to quantify how much uncertainty there is, and codes or coding theory is about maybe trying to study sort of how to provide certainty. So if you are trying to talk to me, the fact that you are talking in English, and you can think of the English language as a code, and the fact that you said something provides me more certainty about what you had in mind. When your algorithm learns some parameters or learns a model, we can think of the model as an encoding of the data, because the data was kind of haphazard, lots of different things, and your algorithm kind of figured out some patterns. So in that sense, I will say it learned something about the data, and that's what we will think of as certainty. So that's also some form of coding. And there are two kinds of coding this way. One is they're just kind of trying to create order. So you have a lot of maybe wild data or lots of uncertainty about what you're going to say, and you're trying to say it as concisely as possible. That's what's called source coding. And then there is also another way of trying to provide certainty when you know what you are going to say is not going to be communicated properly. So of course, what I'm saying to you on Zoom is not communicated properly, partly because I don't encode it correctly. So I'm not saying it in the most precise way always possible, but also just because transmission over the internet is noisy. And so Zoom is using some coding to actually make sure that at least to some extent you receive what I say. Okay, so so the techniques used are somewhat different, but they are kind of dual things to each other. Codes are, we will take the perspective of sort of how to construct codes, and information, we will try to take the perspective of what can be done with codes and sort of what is the best possible at times, etc. So we will try to quantify that mathematically. In this course, we will kind of roughly spend few lectures on basic concepts of information theory. So this will involve things like entropy, mutual information, KL divergence. And as we go along, I'll kind of keep mentioning some applications of each of them. The applications will be sampled from maybe statistics, theoretical computer science, mathematics, maybe a little biased by my personal tastes. And later we will spend some more time on applications, but I'll sort of also try to mention something along the sort of introduction of each concept. After that, we'll take maybe a little deeper dive into statistics and talk of things like, I mean, again, it's not that statistics is always distinct from theoretical computer science. So there will be overlap with things like how to analyze an algorithm or how to prove a large deviation bound for some kind of random thing that you're observing. But I'll think of these things as roughly as statistics, followed by some time on error correcting codes. And in terms of techniques, this part will be the kind of coding theory part of the course instead of the information theory part. But again, as I said, these are not completely distinct, although there will be some separation in terms of what techniques we will study here. And then we will kind of focus on slightly more advanced maybe TCS applications. TCS is theoretical computer science. And maybe some miscellaneous topics. And these are some things I might decide based on how much time we have left. So the last 3-4 lectures might be a little more free in terms of what content we will cover in those. That's roughly the plan for the course. Of course, this is the first time I'm teaching this course online. So we'll see how it goes and how the plan changes as we go along. Okay, and now let me recap some of the mathematical notions that we will need, and then we'll start developing the sort of information theoretic concepts for the course. Any questions on the plan for the course, the content of the course, the format of the course before we start? So there is a question in chat about how do you want us to ask questions. Easiest is just unmute yourself and ask. And if I really don't want to be interrupted, I'll tell you, but don't worry about it. Feel free to unmute yourself and ask a question. Okay. And on that note, please do unmute yourself and ask a question if you have any about the class or the content. Okay. All right, so just a little bit of recap about random variables. I'll also use it to kind of set up some notation that we will need throughout the course. So, I mean, this is not a substitute for any introduction to probability theory. It's barely a recap, if at all. But a notion which is kind of crucial is a random variable and then associated notion of a distribution. So roughly speaking, we can think of having a probability space, which is some sort of space which measures all possible outcomes, or in which kind of we can list all possible outcomes of whatever random processes are happening in our universe, or however you want to define this. But this is supposedly everything we are potentially interested in. And for starters, we will think we can start with discrete or even finite probability spaces. So the space can be thought of as just as a space of numbers 1 to n for some large numbers, and you can assign some meaning to each number. Okay. And there is some sort of measure which kind of assigns some number or some now some real number, or what we will think of as probability, to every outcome in this space. And more generally, when the space is infinite and not necessarily discrete, this measure will not talk about every possible outcomes, but certain allowed set of outcomes, which is what is called a sigma algebra, and is needed to define probability properly for infinite spaces. But right now, let's say, stick to discrete spaces to start with. And a random variable is, it's actually a little bit of a misnomer, as I like to say. So when I teach probability, it's not random and it's not a variable. So it's a function from this outcome space to values. And let's say we are thinking of real values for now. But it could be any set of values. It could be a finite subset of the real values. It could be complex numbers. It can be vectors, or it can be sort of the space of some 5 colors or whatever. It doesn't have to be, or it can be sort of pixels on my screen. It doesn't matter. But this is intuitively what we are interested in observing about the space. So again, when I'm saying sort of a lot of random things are happening, my kind of vocal cords are moving, so hopefully some neurons in my brain are firing, and some of these are, but most of the time you're not interested in all of that randomness, in all the kind of molecular motion that is going on. All you care about is maybe the words coming out. So in some sense, this is the stuff you're interested in measuring, which is the random variable corresponding to English sentences or words coming out of my mouth. So this is what we will think of as the stuff we are actually interested in measuring. And notice, as I defined it, this is just a function on the outcome space. It has no probability associated with it. The space omega is where the probability is happening. Things are happening in some, according to some measure mu on this space omega, and this just, based on whatever happens there, this gives you an outcome. So assuming that sort of all the movements of the vocal cords are completely fixed, the outcome of the words is no longer random. It's just a function of the vocal cord movements. So X is just a function. The probabilistic stuff is happening inside the space omega. And if I have, but because of whatever is happening, because of whatever random stuff is happening inside omega, the values of X also, if you see them, they kind of look random, like they will be distributed in some way over the set of all possible values. And so we will use to sort of, we will say that the distribution of this random variable is P of X, which is whatever kind of behavior happens on the values of this variable or on this function, based on the randomness happening inside the probability space. But I just want to make a little bit of a distinction between this kind of variable and its distribution. These are two sort of, the variable is what I'm going to think of as a function, and then the distribution is something that comes from the measure on the probability space. Now, although sort of there is this distinction, it's sort of, the notation is almost always abused a bit in information theoretic expressions. So a lot of the times, so we will use, let's say, the symbol, and this is an information theoretic quantity h, which I'll define shortly, but you will see an expression which will be of the form h of x. And if you have joined the Slack workspace for the course, the icon is h of x. So strictly speaking, it's actually something which depends on the distribution of the random variable. But most of the time when we are talking of a random variable, the distribution is clear from context, and we'll just say h of x. Similarly, if we have two random variables, the distributions are usually clear. We will just say h of x comma y, or something which just names a random variable. There will be occasionally cases where we will talk of two distributions for the same sort of function x. So this can be coming from two different measures on the underlying probability space. And that will mean we have two different distributions, but the random variable is kind of fixed and clear from context. And these were if you have seen this concept, when you define things like KL divergence, we will talk of two distributions, but one random variable. And we'll come to these, but I'm just sort of preparing you for this notational cheat that I'm going to do all the time, because this is sort of standard in textbooks when you read. So when the random variable is clear from context, often we will talk of only two, like the names of the distributions, but not necessarily the random variable for which they are. And there are sometimes cases when we have multiple distributions, multiple random variables, and then I'll try to be explicit, and I'll sort of say expressions like p of x comma y, or p of x, and maybe q of x comma y. So these are kind of more explicit expressions when I'm writing down distribution and the random variables in question. So, but most expressions that we will develop in this course, and you will see in textbooks, will either just talk about the distribution or the random variable, and then kind of assume that the other is clear from context. And these are sort of coupled. A lot of the time you use just one to describe both things, unless you really need more clarity from context. Just to make it slightly consistent in terms of notation, we will always use things like x, y, z for random variables, capital letters. Random variables will be shortened as random, like RVs. Much less fun than the other RV. Lowercase letters for the values these random variables might take. I mean, I'll not limit to x, y, and z always, but I will use this kind of lowercase letters to denote values. And I will use this sort of scripted letters and these calligraphic letters to denote the set of values. And for the distributions, we will use like letters like P and Q to denote names of distributions. And lowercase letters P and Q to denote actual probabilities. Yeah, always ask me if something is confusing, but I'm just sort of giving a rough notational guide before we start, so as to make sure we at least can, I'll try to stick to this as needed. Okay. For now, we will need to know the basic notation and sort of notions such as the expectation of a random variable, which is nothing but so let's say your space is finite, so then you can just write it as a sum, a weighted sum of the values of this function x at different points in the space. And if it's infinite, then you need to kind of, if it's uncountably infinite, then you need to define it as an integral, which requires a little bit of care. But for now, let's start with this. Okay. I'll come back and say any, I mean, this only makes sense when sort of summation is defined. So let's say the random variable has real values. I mean, it could take in values in any set. It could be taking values in sort of red, yellow, green, blue, and doesn't quite make sense to add sort of blue to yellow. Well, it makes sense chromatically, but not really in any addition sense. Okay. So another notion which we will use, and I'll kind of recap, is convexity. Any questions about probability before we proceed? Please unmute yourself and feel free to ask a question as needed. All right. Okay. So a reminder on convexity, we'll need two sort of objects, a convex set and a convex function. Yeah, I tried to draw a convex set beforehand, but even then it's not a properly drawn shape, but okay. And we say a set is convex if you look at any 2 points, say u and v in the set, then if you look at the line between them, which you can think of by so you can think of the line between them as by adding some multiple of u and some multiple of v, which is called a convex combination if the two coefficients add up to 1 and are non-negative. And we say a set is convex if whenever 2 points are in the set, then the entire line between them is also in the set. Okay. And as we will see in a minute, you can also think of it as a random variable which is equal to u with probability alpha and equal to v with probability 1 minus alpha in some sense. So this notion is very directly related to probability distributions or random variables. Okay. A function is convex if some sense the kind of the area above the graph of the function is a convex set. So another way of saying it is that if you have if you take the value of the function at x, and if you look at the value of the function at y, then you will get this point. And this should lie in the kind of region which is above the graph of the function. And the graph of the function sort of at this point will have the value so the average of the values of the function should be bigger than the value of the function at the average point. This is another definition. This is the definition of a convex function. I mean, there are many kind of equivalent ways of thinking about them, especially when the domain is nice. And in general, doesn't have to be defined on R to the D. You can think of it as being defined on any convex set S. And still ask for the same property. I'm asking for the set to be convex so that this point is in S. Otherwise, it's not clear sort of what point I'm taking the value at in the right-hand side. Okay, so that's roughly convex sets and convex points. There are many other definitions. In particular, if your function is twice differentiable, then the second derivative being non-negative is also a definition of convex functions, at least if it's a function on just on real numbers or a subset of the real line. If it's as a function in multiple variables, then you need to look at certain matrices called the Hessian, etc. So, but for now, let's stick with this definition or use this derivative definition for a function of one variable. And if this inequality is kind of always reversed, then we will call this function a concave function. So, I mean, f is convex if and only if minus f is concave. So you can just flip the value and think of it as a concave function. Okay. And already what I kind of, okay, let's see. What I said here already sort of, as I said, we can think of a random variable which is let's say equal to x with probability alpha and y with probability 1 minus alpha. So notice I'm not writing a lot about the underlying probability space. I'm directly writing the distribution of this random variable, which is how we will work most of the time in the course, unless there are kind of many different random variables assigned on some common space and we really need to understand how they relate to each other. Okay. But if you think of this, then if you look at, if you look at a random variable, let's call it z, which is equal to f of x. So if x is a function completely determined on the outcome space, then so is z. Then the statement we are making is, at least for this sort of baby random variable which takes only two possible values and we know the distribution, that expectation of z, which is equal to expectation of f of x, is greater than equal to f of the expected value of x. This is the left-hand side in the equation. And this is the right-hand side in the inequality, sorry. And this is, we are making the statement that this is true at least for a function with two, like a random variable with two possible values. And this can be generalized to an inequality, which is something which is kind of one of the most useful inequalities we will kind of encounter in the course. This is called Jensen's inequality, and it's the following. So let's say your S is a convex set, and let's say f is a function from this set to say real values. Then and let's say x is a random variable supported on S, which the support of a random variable is just the set of all values it can possibly take. So this random variable always takes a value inside S, never goes outside S. And Jensen's inequality says that if f is convex, then we have that expectation of f of x is always greater than equal to f of expectation of x. Equivalently, if f is concave, then the inequality is flipped. Okay, this, yeah, as I said, is one of the most useful inequalities, and we'll use it repeatedly as we go along. Any questions so far? This is a review of two very basic things that I will need, and then we will now jump into some of the course content. Everyone okay so far? All right. Yeah, it's kind of hard to see everyone's faces at a glance on Zoom, so I can't always tell. In class, sometimes if a student is giving me a very displeased look, then I know that they're not happy. Okay. All right. So we'll use Jensen's inequality repeatedly, and throughout the course, I will assign exercises like this. So the exercises for here, first, prove Jensen's inequality, at least for the case when the support of x is finite. So we already said that the definition of convexity already proves it when the support of x is of size 2. And my claim is you can actually just use induction to prove it for any finite support size. So that's a good exercise to try and do, and just kind of make sure you're comfortable with the statement of Jensen's inequality. Also, just make sure that you're okay with convex and concave functions. In particular, check that x square and x log x are both convex functions. And just notation, in this course, we will always write log base 2. And if we need to write log base e, then we will write ln, or which is the natural log. And if for some reason we need log for some other base, we will specify, but otherwise log x is always log base 2. Okay. And the third is, yeah, everyone, I hope, knows the Cauchy-Schwarz inequality, which says that if you have vectors u and v, then the kind of inner product of u and v is less than equal to the norm of u times the norm of v of the length. You can define it in as much generality as you want. You can define it according to the inner product or the dot product in real vector spaces, or you can define it in general inner product spaces, etc. Let's say you have a finite dimensional space. Try to prove this using Jensen's inequality. So just again, as an exercise, it's a good thing to just get comfortable with Jensen's inequality. For exercises I assign in the course, feel free to ask me in my office hours or the discussion section if some of them don't. I mean, if they don't make sense as stated, ask me right now. But otherwise, if you try them and you're sort of not sure about some part, feel free to bring it up for discussion. But I will be assigning exercises throughout the course. So I recommend trying to do them as we go along and not sort of the night before the final. It will be slightly easier to kind of follow the material if you're regularly working. And most of them should not take too long. Okay, any questions about convexity? Now we'll switch to sort of actual information theoretic definitions. All right. Okay, so our first information theoretic concept that we will talk about is entropy. And roughly speaking, entropy is a way of kind of measuring the information content present in a random variable with some given distribution. So, I mean, there's nothing special about random variable on which we are defining the entropy. Anything is a random variable because whatever we are observing, and if we are sort of, we just said whatever we are interested in observing, we'll call a random variable. So it's just whatever we are seeing in the world. And we are trying to say how much kind of inherent uncertainty is there, or what would it take for me to be completely certain of this, what I'm trying to observe. And this roughly is but to use a pun, is the content of the definition of entropy. But and there is no. Okay, so we'll see, and I'll kind of state the definition in a bit, but let's try to see what kind of things we can try to say about how to measure an information content. Okay. And it's motivated by first kind of binary communication, let's say, although we'll see in a minute that that won't change things too much. So let's say you're kind of talking to me and you only sort of say things in zeros and ones. Don't do that in the class. But let's say if that was the intention, and let's say we had a random variable which could have two possible outcomes. And of course, the classical example is a coin. So it was heads or tails. And here, roughly the intuition is how much, or like how many zeros or ones or how many values would you need to tell me at the very least to be able to tell me the outcome of this coin, which was, let's say, equally likely to be heads or tails. It's a fair coin. Any guesses? So now someone will have to unmute themselves and speak. So please do. But how many zeros and ones do you need to tell me at the very least? Okay, you're typing in chat, but please unmute and speak. All right, okay. So I got an answer even to the general N question, not the 2 question, but let me start with the question for 2. So it seems like if there are 2 outcomes, you have to tell me at least one sort of 0 or 1, which is, say maybe 0 if it's heads, 1 if it tails. Although you have to be careful with a statement which says you have to tell me this. Like so far, what we just described was actually a code. It's just said that you can tell me either 0 or 1, and that's sufficient to tell me what's happening about the coin. We didn't say how that if that is really necessary. But sort of right now we are not talking in terms of a formal proof. Intuitively, it seems necessary because you can almost think of the head as equivalent to a 0 and tail being equivalent to a 1. And if sort of if you want to completely specify heads or tails, you need to completely specify a 0 or 1, let's say. Okay, but this is intuitive. I have not proved anything formally. Okay. And in general, if there were 4 things, you could think of 0, 0, 0, 1, 1, 0, 1, 1. So for 4 things, you will need to tell me 2 zeros or 1s. And in general, for n, you will have to tell me log n zeros or 1s. So here, this is just, as I said, an intuitive guess, but it seems reasonable that if I have information content and if I have 2 to the r outcomes, and we are going to call this n, then the content is roughly r, or otherwise known as log n. So that's again just sort of a heuristic based on what we think is what we absolutely need to communicate. But then the point is, in any kind of formal mathematical way, if you want to say that you at least need to say the information content is at least this much, we need to make some assumptions about it. So this is not the assumption with which the definition of entropy was kind of created, but this comes out of those definitions. And more generally, if you read Shannon's original paper, which is actually a very nice paper and linked from the course webpage, I recommend taking a look. It kind of develops the definition of entropy from 3 assumptions, which and then the kind of outcome comes out, sort of the actual definition comes out to be a generalization of what we are saying here. But Okay, let me check something. Yeah. So the three assumptions are sort of, two of them are relatively mild. The third is the maybe more interesting of those assumptions. But let's say we had some general distribution. The values were P1 to Pn, and we were trying to define this information content as a function of all these numbers, P1 to Pn. The first thing is the information content should not depend on A1 to AN. It should only depend on P1 to Pn. Just we don't care about what the outcome is. We just sort of are trying to quantify uncertainty, and the uncertainty between kind of this red and green is the same as the uncertainty with between heads and tails if the probabilities are the same. So that's the first thing. So, but the assumptions were that, okay, you want something which is a continuous function. Of P1 to Pn. So first of all, it's only a function of P1 to Pn, and it's a continuous function, which means that if you change things a little bit, it should not really change the definition of whatever is the information content by too much. Okay? It should be also change it only a little bit. The second was if I just sort of think of this kind of uniform distribution or sort of equally likely n outcomes. So, so whatever, if I look at and if I get some function by plugging in all P1 to Pn as equal, then whatever I get should be an increasing function of n. Okay, so intuitively, if I'm sort of completely undecided between two outcomes versus completely undecided between 20 outcomes, then the information content you get from one of those, like choosing one of those 20 outcomes, is more. And the third one actually is the kind of more interesting assumption, which is sort of also generalizes this. It's what I'll call bundling or bucketing. So I'm not stating these very formally, but you can take a look at the paper, and based on that, there is a definition that is developed. But which is just saying that suppose I had three outcomes, but I'm kind of viewing them as sort of making these choices sequentially. So either I can make this choice one of three choices, or I can kind of make this big choice with probability P1 plus P2 and then kind of make individual choices, or make directly this choice. Okay. And the information content should be the same in both cases, or rather, if you think of, so here I will think of the information content revealed by the first choice plus P1 plus P2 times the information content revealed by the second choice, because by the second choice, because you only get to the stage of making the second choice with probability P1 plus P2. So, so I'm going to use the letter H, but so if I make a combined choice in one shot, or I make it in two steps, the information content should be the same. And that's what I'm calling the bucketing property. I don't think Shannon called it that, but or the bundling property. Okay. And under these three assumptions, we kind of tried to see what is a reasonable definition. And turns out if you make these three assumptions, up to like a constant in front, there is only one function that you get. And Okay, so before we go there, let me just add a page. Okay. So we define this function sort of h of x as pi log 1 over pi, where let's say x, then I is equal to 1 to n. So we are going to look at right now uniform, like, or sort of a finite set of outcomes. The distribution is that the values are p1 to pn, and so that defines this distribution p of x. But as I said before, we are already cheating in terms of the notation. We are just saying h of x rather than h of p of x. But this sort of cheat will be common in all textbooks and throughout the course. So at some point, we'll have to get used to it and might as well start now. Okay. Okay, just a quick check. This is always non-negative. Okay, so log here is log base 2. You can actually take it to be log to any base you want. That will just change, just multiply the function by some constant. And as I said, we are intuitively thinking that we are going to communicate zeros and ones. So log base 2 makes sense in there. And just as a quick check, if if you have all probabilities equal to 1 over n, then h of x is equal to which is log n. So this is roughly corresponds to our intuition before in terms of communicating zeros and ones. But first of all, we could have communicated sort of 0, 1, and 2 at each point. And so the log could have been to a different base. And in general, the axiomatic development said that sort of, like what's derived in Shannon's paper is that up to a constant in front, this function is unique. You can choose some other constant if you like. Okay. Again, these assumptions were sort of somewhat arbitrary, but not unreasonable. And of course, if you don't want these assumptions, then there can be some other way of measuring information content and which can be useful for whatever other application you might have in mind. This is just one, and there are other things called, this is called Shannon entropy, by the way. We'll just call it entropy. There are also things called Renyi entropies. There is something called min entropy. And these are all different definitions of entropy which are used. But the most common by far is Shannon entropy, and that's the one we will kind of mostly deal with in this course. Any questions so far in the definition? Just okay. So I'll usually just give proof sketches, but let's say we'll try to do proof in some detail right now. We already proved that it's greater than or equal to 0. That's because it's a weighted sum of numbers, and each number is a log of something bigger than 1. The PIs are between 0 and 1. So this is always non-negative anyway. And the upper bound of log x size, which is just log n. Okay, this is just a good exercise in sort of Jensen's inequality. Let's do it once. So let's say a random variable, we look at a random variable y, which is equal to let's say the value ai with probability pi. Okay. Oh, sorry, which is equal to 1 over pi with probability pi. Okay. So it's a random variable which takes real values, non-negative real values even. Okay, and the zero values occur with probability 0, so we can just ignore them, and let's think of values which occur with non-zero probability. And let's think of the function f, which is log, and it's a concave function, remember? This was one of the exercises, so check that. But then Jensen's inequality tells us that expectation of f of y is less than equal to f of the expected value of y. And let's check both sides. So the left-hand side is summation over I, pi. With probability pi, we get the value 1 over pi. And on the right-hand side, we get expected value, which is with probability pi, we get the value 1 over pi. Okay. And then we just plug in f as logs. So we get summation over I, pi, log 1 over pi is less than equal to f of n. F is log. So. Okay. Everyone's is happy with the proof. Okay. That's just the introduction to entropy. Yeah, if you have any questions, please unmute yourself and ask. Otherwise, we can go on to talking, sort of doing more with this entropy function. Okay. Now we will try to sort of say something formal about if you want to communicate heads or tails, or if you want to communicate certain outcomes, you will have to say at least as much as log n for n outcomes, or in general, the entropy of whatever random variable we are trying to measure the uncertainty of, or we are talking about. And this is measured by, this is a subject of what is called source coding, or where the source is just some random variable, which is giving us some things which are uncertain, and we are trying to communicate it, and the communication is trying to provide certainty about that outcome. So it's a code. And it kind of is a mapping from the possible values of the random variable to sigma is some finite alphabet. In which we are choosing to communicate. It can be the English alphabet, it can be just 0 or 1. It can be the alphabet of your favorite, let's say, written script for now, but so it can be any sort of finite set. And sigma star is the set of sequences of any finite length, but not necessarily all of them the same length. So the star kind of denotes so you can say sort of a sequence of length 2, length 3, all of them are in sigma star, or sort of whatever finite length you want. And different sequences can be of different length. Okay. And we will try to communicate using what is called a prefix-free code, which means that which kind of ensures, to quote a TV show, that you got nothing coming. So in some sense, it never happens that you sort of hear a code word, and after that, you're not sure that, okay, has the code word ended? Am I done? This is the sequence. Or there is some part of it which will be another sequence. So suppose you have a list of all possible sequences, or all possible sequences that appear in this in sigma star that appear as part of this code. Okay? This code is just a function. So we are just thinking of the image of this function. And the question is, you got some sequence. It's one of the possible things that is in the image set. So you know that it corresponds to some x as a possible value of the random variable. The question is, can it correspond to more than one? Is it possible that after that I will add some sort of follow-up sequence, little sigma, that it will actually then correspond to the image of y rather than the image of x? Okay. And prefix-free code is a setup or is a collection of sequences where this doesn't happen. So at any point, if you got something which is a valid image, just stop. You will not be able to add anything to it to create another valid image. And the list of all valid images is called a code word. The list is the code, and each valid image is called a code word. Okay. So each image is called a code word. Okay. So any questions about the definition of a prefix-free code? I mean, not all codes that we will consider will be prefix-free code, or not all of them have to be. It's just the choice we are making at this point, because prefix-free codes are ideal when you want to communicate sort of many things one after the other. So suppose you're not just trying to communicate one outcome of this random variable, but many outcomes. So at some point I have to know when you stopped communicating the first outcome and then started talking about the second outcome, and so on and so forth. And with prefix-free code, there is never any confusion. Once I get something which is in the image, I know you have communicated one outcome. Then I start waiting for the second outcome. Otherwise, I would not know when to stop thinking about the first outcome and start thinking about the second one. There can be another way this would be easy to ensure. I can say that all images are of size 20. And so whenever I receive 20 bits, I'll stop. And for now, we will start with the prefix-free codes, though not necessarily everything has to be of this flavor. Okay. Mm-hmm. And those are sort of codes of fixed block length, and we will see in error correcting codes. And within this framework of prefix-free codes, we will try to kind of provide a framework to say what an information content is, and sort of how to say that entropy tells us how much content is there in a variable. And we will think of, just as I said, we will be thinking of talking about zeros and ones. So think of sigma as zeros and ones. And so we will either say a 0 or a 1. And now the goal is to given this random variable x, whose values are in this set script x. So it's supported in this set script x. Let's say there is a distribution there's a distribution P. Sort of a design code with so different sequences can have different lengths. So it's not clear how to measure the shortest code. And right now, the way we are trying to measure it is just saying that the expected number of bits we communicate the expectation is over all possible random outcomes of the random variable according to its distribution. The expected number of bits we communicate, or the average length of the sequence we communicate, is small. Again, this is not the only way to measure it. This is what we are going to use right now, but it depends a little bit on what applications you have in mind. So for all of these choices, there are some canonical ones that are most common, that are used most typically, but that's not to say that they are the only ones. But I will use the ones which are most common for now. Okay, and to be able to say something formal about prefix-free codes, we will use this inequality, which is called Kraft's inequality, which characterizes when can it happen that you are given a sort of n sequences, which are of lengths L1, L2, all the way to Ln. When do these lengths correspond to some prefix-free code? So what property do you need on these numbers L1 to Ln so that they correspond to lengths of some code words in a prefix-free code? And it's actually a tight characterization. It says that you have a prefix-free code with this sort of lengths if and only if these lengths satisfy the inequality that 1 over 2 to the Li is less than equal to 1. Okay. And so as the statement suggests, there are two parts to it. One, if this happens that 1 over 2 to the Li is less than equal to 1, then we can find a code which has exactly these lengths. And an only if part that no matter what code you gave me, the lengths have to satisfy this property. Okay. Okay. At this point, someone has to tell me whether you want me to prove the if part or only if part first. For future future reference, I will often only prove one of them, so choose wisely. But right now, since we are starting, I'll prove both of them. But you can tell me which one you want me to start with. Someone please unmute and speak. Let's at least hear some voice.
If.
Okay. All right. So let's prove the if part first. So if we are given L1 to Ln such that 1 over 2 to the Li is less than equal to 1, then there exists a code. Okay. The code is prefix-free, etc. It's over the 0-1 alphabet. And so. Okay. So let's say L star is the maximum of these lengths. So, and I'm now going to sort of give a procedure for constructing such a code, which will be prefix-free. And yeah, the only thing I will use is this inequality that we know is true, like that we are assuming is given on the lengths. Okay. And the way we will prove it is that think of all possible sequences okay, so whatever is the longest length, and actually, yeah, let's say we also sort. So we will start with the smallest length first, and then keep going to the larger and larger ones. Break ties arbitrarily. If two things are equal, just pick whichever you want first and then the second. But we will start in the increasing order. And now each node in this tree can be thought of as a sequence of length less than equal to L star, and the leaves can be thought of as okay, so let me say why, but you can think of, let's say, every time you branch left, you think of it as a 0. Every time you branch right, you think of it as a 1. Okay, so if you are here, then you are talking about the sequence which is 0. Okay. And each time you branch left, you think of it as a 0. Each time you branch right, you think of it as a 1. So if you are here, you are thinking of the sequence 0, 1, because you first branched left and then right, and so on. So each node kind of has an address in this binary tree where every node has 2 children, and it's sort of the address based depends on what edges we took from the root to get there, and each edge is labeled with a 0 or 1. So when we write down its address, it's a sequence of zeros and ones. That's a string. And at the bottom, we will have an address which is L star bits long, or we will have taken L star edges. So that's the construction of the tree. Is everyone okay with about the definition of the tree? And then we'll just say that each code word will be a node in this tree. We will start kind of picking and sort of hacking away different parts of the tree or cutting branches and so on. And that will give us a code. Okay. So to construct a code, let's say the L1 to Ln are sorted. So we start with the shortest length. Let's say L1 is the shortest length. Okay. So we pick a node at distance L1. Okay. And we kind of, if we pick the node at a distance L1, that just means we kind of picked a bit string of length L1, and we are just going to call this one of the code words. So okay. So one code word is L1, is whatever string we picked here. Because it's a prefix-free code, you cannot add anything to this string and think of it as another code word. You're not allowed to follow it up with anything else ever to get a valid code word, which in the tree kind of language means that all the children and their children, sort of the entire tree from this point forward is just no-go. We are not allowed to pick any sequence below this, right? Because to get to any node below this, we will have to make the same choices first to get to L1 and then get to points below this. There is no other way to get there. So, so we're just going to say that we'll delete it. And then for L2, we will pick something in the rest of the tree, and so on. Okay. Now, the entire proof is the answer to the following question. What is the fraction of leaves we have deleted so far? So what is the total number of leaves, first of all? It's 2 to the L star leaves, right? Because for every choice of 0, 1, we can make L star choices, we have a leaf. So the total number of leaves is 2 to the L star. And now let's think of L1 as 1. So it was either 0 or 1, just some one of them. Okay, like L1 is 1, and we made a choice, which was we either deleted the left half of the tree or the right half of the tree. So the fraction of leaves deleted was half, because we deleted left half or right half. If L1 was 2, then we kind of went too deep, or sort of depth 2, and then we deleted the tree there. So the fraction of leaves deleted so far is 1 over 2 to the L1. Depending on how deep we went, the fraction kind of kept reducing. Okay. But if we have deleted 2 to the L1 leaves so far, summation 1 over 2 to the Li is less than equal to 1, which means that there are some leaves left. And if there is a leaf left, there is a path of every length from 1 to L star left, because a leaf is kind of at the largest distance possible. So we can continue. So okay. And so this is the construction of the code. We will pick L2. There are some leaves left. We will pick some node in the remaining part of the tree, which is at distance L2. If there is a leaf, there is something above that leaf. So there is, in particular, a path of length L2. Remove it. Now we will delete an additional 1 over 2 to the L2 fraction of the leaves. Total fraction deleted is 1 over 2 to the L1 plus 1 over 2 to the L2. That's still less than equal to 1. So there are some leaves left. Repeat. Okay. Any questions about this proof? Okay, so let me quickly do the other side of the proof, and then we will stop here for today. Okay, so let's do the only if part, and I find it kind of convenient to think about it in the language of probability, but you can actually also think about it in terms of that tree. So so, I mean, yeah, okay, let's think about it in terms of the tree, and then I'll state the probabilistic version. So now what you are is, you are given a prefix-free code, and lengths are L1 to Ln, and then we want to prove that summation 1 over 2 to the Li is less than equal to 1. Okay. And again, because this tree can be thought of as the set of all sequences of length all the way up to L star, which is the maximum, you can sort of situate any code word on this tree. So given a sequence of length L1, we can, I mean, now the sequences are given. It's not just that the lengths are given. We are given a code. So given, let's say, the code word C of x1, it's some sequence. Let's say the sequence was 1, 0, 0. So we can find 1, 0, 0 on this tree and mark that node. And again, because we are promised that it's a prefix-free code, we know that this node kind of disallows the fraction of leaves which come below it, or all the leaves that come below it, because it's a prefix-free code, so I can't kind of go any further in this path. So, and so let's say that let's say C of x1 controls these leaves. How many are there? Well, again, 1 over 2 to the L1 fraction. Again, the same argument. It's just counting the number of binary strings of length L star minus L1, which will be left to go below. And the kind of the proof is finished by just observing that set of leaves controlled by each code word should be distinct or disjoint. For each valid code word, because it's a prefix-free code, so you can't have any sort of overlap between what can potentially come after the C of x1 and what can potentially come after C of x2. So it's the same proof, just run in the reverse direction. But because these are disjoint, the total fraction of all these leaves must be 1, because, well, it's just a way of writing down all the leaves of this tree. Each leaf is controlled by at most one C of x. Note that. Another way of thinking about is probabilistic, that, well, you were starting and you were kind of tossing coins, zeros or ones, and you tossed L coins, and you kind of stopped every time you saw something which was a valid code word. Okay, so we can think of an event that your coin tosses sort of kept going until you received the first code word, or the coin tosses kept going until you received the second code word. You can check that the probability of any code word is of length Li is 2 to the minus Li. And these are all disjoint events, or you cannot receive one code word and continue on to another code word because of prefix freeness. So the summation of all the probabilities is at most 1. That's just a different way of saying it in a sort of more probabilistic terms rather than this graphical. Okay, I'll stop the class here for today. If you have time, I'll be in the gather space for the course in case you want to hang out there or just get used to the space. I'll be there for the next few minutes. Feel free to check it out. The links are on Canvas and so on. Otherwise, I'll see you on Thursday.
Thank you.